So hello everybody, I am Vincent Cecchini from the KM3NeT collaboration. And today I will present you the online analysis framework that we have developed to do multi-messenger analysis astronomy with the KM3NeT detector. But first of all, I would like to thank the organizer for granting me with this talk. And I will start by a really quick slide on the multi-messenger astronomy because all of you know what it is. So we have a wide field of topics which are being covered by multi-messenger astronomy. And me, I will focus on the neutrino because it is what we are doing with KM3NeT. And neutrino can be great messenger to do multi-messenger astronomy, as it has been told in the previous presentation. So KM3NeT, now, it is a collaboration gathering 20 countries and 47 institutes, mostly spread over Europe, but not only. And we have two detector sites, one offshore here of Sicily, which is ARCA, standing for Astroparticle Research with Cosmic in the Abyss, and another site offshore of Toulon, Mediterranean and France, which is ORCA, standing for Oscillation Research with Cosmic in the Abyss. So what you have to remember is ARCA is for astroparticle and ORCA for oscillation, but we can do also astrophysics with both. I will detail that later. So about the detectors, what is the difference? First thing you have to know is with KM3NeT, we have the same technological cell used both for ARCA and ORCA, which is to know the DOM, digital optical modules. So we are using a sphere filled with 31 PMTs, and we put 18 of these DOMs to form one detection unit, so one line. And we will then gather this line in building blocks. So 115 detection units will form one building block. So what is the difference between ARCA and ORCA? As you can see here, it is the size of the detector. So we have the same number of PMTs in one building block, but ARCA will be formed by two building blocks, while ORCA will be formed by only one. This is because looking at oscillation requires to look at lower energies than doing astrophysics. So we have the ARCA detector, which is quite depth in the sea at 3,450 meters. ORCA is at 2,450 meters. ARCA is optimized at energy above the tera-electron volt, and ORCA is optimized for energy between the giga-electron volt and the tera-electron volt. We can also look for neutrino at the mega-electron volt by doing analysis on single DOM, multi-ins on single DOM, which is useful for looking at neutrino from supernova. And so it will result in different size of instrumented volume. So 1 gigaton for ARCA and 7 megaton for ORCA. The construction of the detector. We are quite young detector. We are starting the building in 2015 for ARCA, 2017 for ORCA. The phase one of the detector building has been achieved, and now we are at 20 DU deployed for ARCA and 18 line deployed for ORCA. Well, I have an update from this weekend. We have put one more line for ORCA, but due to the weather, we have not connected. So yeah, it is still ongoing. And the completion of the full detector, so 230 lines for ARCA and 115 for ORCA, is foreseen for 2028. But we are already taking data. And here you can see one muon track being reconstructed with ORCA 18. So how are we doing the physics? We are using the Cherenkov light cone produced after the interaction of the neutrino. So it's a particle, if it is a muon neutrino, it will produce muons then. And this muon traveling faster than light in the water will create Cherenkov light. And with our PMT array, we will try to detect it. So as for IceCube, we have different topology, different event topology. So we have the track-like event, doing a beautiful straight line over the detector. We have the shower event corresponding a bit to the cascade, if I understand well. making lighting cluster of PMTs inside the detector. And we could have double bank tracks from tau neutrinos or from tau particle or from exotic physics. As for what concerns us for astrophysics, we are interpreting the downgoing tracks, so tracks coming from the atmosphere and pointing to the Earth, mainly as background. We have a sharp cut on this downgoing track, so we are looking mostly at the events which are upgoing. Then, what do we want to do with KM3NeT in the multi-messenger astronomy? So first thing we want to do, and we are already doing, is to follow some alert brokers to do high energy follow-up of external sources, which are detected by IFIC, for instance, by Fermi and by other detectors. So we are triggering an alert from this external broker, looking for a neutrino counterpart in our data. And if we find something, so we hope at some point provide some results, and maybe we can help to refine some position for gravitational wave event, for instance. And then the second thing we want to do is to be able to send our own alert, so detecting interesting high energy neutrino candidates in our data, and provide an alert to the community through the GCN network for our high energy searches or through SNews2 network for core collapse supernova. So how are we doing this multi-messenger astronomy? First, we have to know that it is a combination of a real-time analysis framework. So this RTF framework in KM3NeT is run to reconstruct the event as a track, as a shower, and to classify the event as a muon or as a neutrino. And then the output of this RTF framework is provided to the KM3NeT online analysis pipeline. And here we will run the physics analysis, point source analysis, gravitational wave analysis, core collapse supernova, etc. And the aim of the analysis is to look at spatial and temporal coincidences between the KM3NeT events and the active astrophysical source that have triggered the analysis. So as I said, we are doing two main kind of analysis, the high energy one and the analysis at mega electron volt for core collapse supernova. So the high energy analysis, I will come back to that later, but it is on-off analysis. We are setting a cone search, and the event selections then depend on the kind of trigger. So to give you an idea of what paths follow the data, first they are produced at the detector and sent to shore. In parallel, they are reconstructed at the ARCA shore station and at the ORCA source station, the real-time analysis framework run. Everything is broadcast to the multi-messenger dispatcher, where we will have analysis within our data to look for interesting neutrino candidates. And the multi-messenger dispatcher will receive also and listen to this external alert. If needed, it will trigger the online analysis pipeline, which will run the point source, which will run the analysis. And then the data will be sent back to the multi-messenger dispatcher for further broadcasting if needed, so internally or externally at some point through notice one day and through circular if needed. To give you an idea of the time that all the process is taking, so for ARCA, the reconstruction as track and as shower, as well as the classification, are running parallel. So each process took about 4 seconds. So after 4 seconds, we have reconstructed one event for ARCA. While for ORCA, everything is done in series, so it takes about 6 seconds. We have a rate about 10 Hertz for ARCA, about 20 Hertz for ORCA. It is due to the difference of depth of the two detectors in the sea. And with the full detector, we are expecting 100 rates, about 100 Hertz rate. Okay, I have said later before that I will come back on the reconstruction of the event technique. So as I said, when we have an interesting event to analyze, we are setting a cone search analysis. So we take the localization of the trigger, and at this elevation, we will select a band of the same elevation. our event will form the signal region, which will be the on region. It is a space region at the time of the event. And then the off region, it is the band around at the band at the same elevation than the event, and not at the time of the event. So we will look at the data of the 1 or 2 previous week that we have. From this off region, we will then estimate the number of events that we are supposed to have as a background in our on region. So we do that by counting the number of events we have in the off band, multiply by the duration of the on region, divided by the duration of the off band, so 1 or 2 weeks, and multiply by the surface of the angular that we have. And then we compare this, the number of events we actually have in the on region to the number of background events that we are expecting in this region. And we have some p-values that we can after a podcast. For now, this analysis are performed only with track-like event, but we are working also to include the shower-like events. So now the follow-up. It is working since in production mode since 2022, in November 2022. So from November 2022 to June, we have received more than 300 GRBs, 22 transient alerts, 57 ice cube alerts, and 154 gravitational wave alerts. But this is only from the start of 03, so only in 2 months. We are receiving the alert from the GCN, with the Apache Kafka protocol. We are also working on the implementation of additional brokers such as TNS, Microquasar, Flaplook, which should come quite soon. And when an alert arrives, it triggers all sky analysis, both for ARCA and for ORCA, as well as a MEV analysis. Then we get some output from this, like the version of the analysis, the number of background events, the observed number of events, etc. All these data are shown internally to KM3NeT on a web page we have developed, which is a shifter tool. So here on the left, you can see the sky map of the alert of last month, the list of alerts received. And when you go to the link to the analysis, here you have the output of the analysis. So all the number, the position of the alert, and the output of the analysis, and few plots. What are we doing with this result? We may broadcast them. So for now, if we have some interesting follow-up, or if an astrophysical events have been notable enough, we will publish a circular, or a GCN circular, or an astronomer telegram. And we can also set up a refined offline analysis. And in the future, if we detect some interesting high energy neutrino candidates, we will send a notice through GCN or through SNEWS. SNEWS for CCSL. So here an example of the follow-up of GRB 221009A that have been presented yesterday. So as it has been said, it is a really powerful GRB. So there has been a worldwide follow-up campaign. KM3NeT have been involved in that. We haven't found any excess signal, but we have published this not finding in a circular. And we have also set up an offline refined analysis, which have not found anything too. And more wider, we are not doing only online follow-up with KM3NeT. We are also doing more general astronomy stuff. So here you can see a search we have performed with the data of 2021 and 2022 from ARCA for searching for a diffuse neutrino flux from the galactic center. We haven't found any excess over background, and we are not yet competitive with the limits set up by Antares and mainly by IceCube. But we have good perspective because the detector is still growing, and we hope to be more performant on that. I will show you that on the next slide. And at the bottom, you can see here the sensitivity for point source analysis. So we have selected 101 sources at PEV energies. And then we have performed a point source analysis. So here again, no significant neutrino have been observed. The sensitivity is still a factor 4 from the interest sensitivity. And what I have to say is, again, the astronomy potential is rising fast with the growth of the detector. So what can we expect from the growth of the detector? On the left, you have the diffuse analysis, the confidence level for a discovery of the diffuse neutrino flux from the galactic ridge, and the 5 sigma discovery would be reached in half a year with the full ARCA detector. And for the point source analysis, here KM3NeT ARCA 230 is in black. So you can see that the point source sensitivity would improve over the full sky, and we will also get unprecedented sensitivity in the southern sky. So I will conclude by saying that we have now a real-time analysis framework which is working quite well for KM3NeT. We are performing online follow-up. We have already sent 3 GCN circular and 1 astronomer telegram. The alert sending process is still in progress, and the detector growth will bring some exciting detection capabilities. So thank you, and if you have questions, I will be glad.